Disclosure. This educational content has been developed using artificial intelligence.
Ever wondered how that tiny blue dot on your phone knows exactly where you are? Down to the very street corner? It feels like magic. Right? But it's not magic. It's a brilliant piece of technology called the Global Positioning System, or GPS. Today, we're going to demystify it together. How does this incredible system, which we rely on for everything from finding the nearest coffee shop to navigating cross-country road trips, act which you work? Let's dive in. First, let's get the basics straight. The GPS system is actually made up of 3 parts. The first part is the space segment. Imagine a constellation of about 30 satellites orbiting the Earth. These aren't just any satellites. They are incredibly precise instruments, each carrying multiple atomic clocks. They fly in very specific orbits, about 20,000 kilometers above us, completing 2 full orbits every single day. This network ensures that from any point on Earth, at any given time, at least for satellites are visible in the sky. These satellites are the bedrock of the entire system, constantly broadcasting signals down to us. So, what are these signals they're broadcasting? Think of it like each satellite is constantly shouting, "It's exactly this time, and I'm right here." More specifically, each satellite sends out a radio signal that contains 2 key pieces of information: the precise time the signal was sent, and the satellite's exact orbital position at that moment. These signals travel at the speed of light, zipping through space and our atmosphere to reach the ground. And this is where the second part of the GPS system comes into play: the user segment. The user segment is, well, or more accurately, your GPS receiver. This could be your smartphone, the navigation system in your car, a smartwatch, or a dedicated handheld GPS device. This receiver is the listener in our scenario. Its job is to pick up the signals from those satellites high above. When your phone's GPS is turned on, it's actively listening for these pings from space. The magic happens when your receiver picks up signals from multiple satellites at the same time. Now, for the really clever bit, trilateration. It sounds complicated, but the concept is quite simple. Your receiver calculates its distance from each satellite by measuring the time it took for the signal to travel from that satellite to you. Since the signal travels at the speed of light, a known constant, the signal itself tells you when it was sent. Your receiver can do a quick calculation. Distance equals the speed of light multiplied by the travel time. Let's visualize this. If your receiver gets a signal from one satellite, it knows it's somewhere on the surface of a giant, imaginary sphere with the satellite at its center, and the radius of that sphere is the distance you just calculated. That's a huge area. Not very helpful yet. But now, at a second satellite, your receiver does the same calculation and figures out its distance from this second satellite. Now you know you're on the surface of 2 different spheres. The intersection of these 2 spheres isn't a point, but a circle. We're getting closer, but we're still not at a single location. This is where the 3rd satellite comes in. Your receiver calculates its distance from a 3rd satellite, creating a 3rd sphere. When you intersect this 3rd sphere with the circle created by the first 2, you get just 2 possible points. One of these points is usually somewhere ridiculous, like thousands of miles out in space or deep inside the Earth, so your receiver can easily discard it. The other point, that's your location. This is the core principle of 2D, positioning, finding your latitude and longitude. So why do we always hear you need for satellites? The 4th satellite is the key to both 3D positioning and incredible accuracy. It helps determine your altitude, telling you how high you are above sea level. But more importantly, it solves a huge problem: time. Remember how the whole system relies on knowing the exact time? The satellites have ultra-precise, mind-bogglingly expensive atomic clocks. Your phone, on the other hand, has a cheap quartz clock, which is pretty good, but nowhere near accurate enough for these calculations. Even a tiny error of a microsecond 1/1,000,000th of a second could throw off your location by 300 meters. This is the genius of using a 4th satellite. Your receiver knows there's an error in its own clock, so it uses the signal from the 4th satellite as a reference point. It essentially solves an algebra problem with 4 variables: your latitude, your longitude, your altitude, and the precise time. With 4 signals, it can solve for all 4 in them, effectively correcting its own clock's error and pinpointing your location with remarkable accuracy, often within a few meters. Now, you might think that's the end of the story, but there's one more crucial element. The control segment. This is the third part of the GPS system. It consists of a worldwide network of ground stations that monitor the satellites. These stations track the satellites' flights, check their health, and make sure their clocks and orbital data are perfect. If a satellite's orbit wobbles slightly or its clock drifts, the control station sends up corrections to keep the entire system running with an accuracy that would make a Swiss watchmaker jealous. Without these unsung heroes on the ground, the GPS system would quickly become unreliable. But wait, there's more. What about when you're in a city with tall buildings, or a dense forest, or even a tunnel? These can block satellite signals, a phenomenon known as urban canyons. This is where modern GPS receivers get even smarter. They use something called assisted GPS, or AG. Your phone can use cellular network data to get a rough idea of your location much faster than waiting for satellite signals alone. This initial hint helps the GPS receiver lock onto the correct satellites more quickly. Furthermore, many devices now combine GPS data with other sensors. The accelerometers and gyroscopes in your phone can track your movement and direction, filling in the gaps when the GPS signal is weak or lost entirely. This is dead reckoning. It is why your navigation app can often still track you for a short while after you enter a tunnel. It's not magic. It's just your phone making a very educated guess based on your last known position, speed, and direction of travel. And we can't forget about Einstein. His theories of relativity are not just abstract physics concepts. They are essential for GPS to work. There are 2 relativistic effects at play. First, due to special relativity, because the satellites are moving so fast relative to us on Earth, their clocks actually appear to run slightly slower. Second, due to general relativity, because the satellites are in a weaker gravitational field than we are, their clocks appear to run slightly faster. The effect from general relativity is stronger, meaning the satellite clocks actually gain about 38 microseconds every day compared to clocks on Earth. It sounds tiny, but if it weren't corrected, GPS navigation errors would accumulate at a rate of about 10 kilometers every single day. The system would be useless within minutes. So, the engineers who designed GPS built these relativistic corrections right into the system's calculations. Your phone is literally doing Einstein's math every time you look up directions. So, let's recap. A constellation of satellites, each with an atomic clock, continuously broadcasts its time and position. Your GPS receiver on the ground picks up these signals from at least 4 satellites. By calculating the time delay of each signal, it determines its distance from each satellite. Using this information, it performs a 3D trilateration calculation, which is corrected for clock errors and even the effects of Einstein's relativity, to pinpoint your exact location on the globe. And all of this happens in a fraction of a second, silently, inside that device in your pocket, the next time you pull up a map on your phone to find your way. Take a moment to appreciate the incredible symphony of physics, engineering, and mathematics happening behind the scenes. It's a network of satellites orbiting miles above ground stations, monitoring their every move, and a powerful little computer in your hand, all working together to place that little blue dot right where you are. Thank you so much for joining me on this journey into the world of GPS. I hope you found it as fascinating as I do. If you enjoyed this video and learned something new, please give it a thumbs up. And do you wanna forget to subscribe and hit that notification bell so you won't miss our next deep dive into the technology that shapes our world. See you in the next one.